All right, let's take a look at the Chapter 6 multiple choice review. And we're going to start with some calculator work because we want to find the expected number of cell phones in a household in Tower Hill. And we want the variance. And so for both of those, what we need is to go to stat edit, stat enter, and then we need to put in the W, the top row, into our calculator in list 1. And we need to put those probabilities into list 2. I'm just going to double check and make sure I have them all right. And then to get both values, we want to do stat calc, one var stats, and I want my list to be L1, my frequency list to be L2. If you have the other kind of calculator, then your command will look like this, one var stats L1, comma L2. And then my mean is my X bar value on the top here. And my variance is not on here. So for letter A, I want 2.55. For the variance, I need to take this standard deviation, 1.32, and square it. So then the variance I want is 1.74. So A is my answer for number 1. C is my answer for number 2. All right, let's look at the next 3 questions here. In a particular game, a fair die is tossed. So that means it has 6 sides. All 6 sides are equally likely. If the number of spots showing is either 4 or 5, you win $1. If the number of spots showing is 6, you win $4. And if the number of spots showing is 1, 2, or 3, you win nothing. Let X be the amount that you win. So let's be careful. First of all, in other games we've done, there's profit that we've been trying to find the expected value. And here it's not profit. Here we are looking at just winnings. So let's set up here our little table. If I don't win anything, I win 0. If I roll a 4 or a 5, I would win $1. And the grand prize here would be if I roll a 6, and that would be $4. And then in terms of probability, if I roll a 1, 2, or 3, then I win nothing. If I roll a 4 or a 5, so 2 out of 6 ways that I would win $1, and there's only 1 out of the 6 ways that I win $4. And this is what I'm going to enter in as my probability distribution. So calculator time again. Stat enter, 0, 1, and 4, my winnings go in list 1. And 3 over 6 is the probability for 0. 2 over 6 is my probability for $1, and 1 out of 6 is my probability for $4. And just like before, we're going to do stat calc, one var stats, L1 and L2, or if you have the other kind of operating system, L1, comma L2. And my mean in this case, my expected value is $1, and that's what they want for number 3. My standard deviation for X is 1.41. There we go, $1 and $1.41. Then question 5 off of this, how much would you have to charge for it to be a fair game? Well, with a fair game, we would want an expected value of 0. So we would have to think about if we subtracted the cost of playing, what would that do to my overall profit? I would want the profit to be 0. Well, if my expected winnings is $1, and then I charge $1, that would give me an expected profit of 0. So we would want to charge $1 to make this a fair game. Number 6, X and Y are random variables and A and B are constants. Which of the following statements is true? Well, A is never true. There is never a time where we can take a standard deviation or get the new standard deviation by adding the old standard deviations. So that's definitely out. B is true, but we need this little fact from the first one. So we can only combine variances or standard deviations if we know that the two variables are independent. So B is not true because they didn't say anything about that. C is, we also have an issue, or actually this would be just multiplying by a constant, so we wouldn't need them to be independent, but if we were going to find the new variance, multiplying by a constant, this should be b squared, and the variable is actually a plus bx, but the standard deviation and variance wouldn't be affected by the a part. When you're adding a constant, that only affects the mean. So this is close to being true, but it would need a b squared to be correct. D, we're looking at the variance of x minus y, but this is correct. We would take the variance of x plus the variance of y, and then they have the second part that we need, but only if x and y are independent. We can only combine random or add standard deviation or add variances if we know that the variables are independent. And E is close. E would be exactly what we would do if that little squared weren't there. The standard deviation of x minus y would be the square root of the variance squared plus the variance squared. But they had variance, so that would not be correct. So 6 should be D. 7. A vending machine operator has determined that the number of candy bars sold per week by a certain machine is a random variable with mean 125 and standard deviation 7. His profit on each bar sold is 25 cents, and it costs him $5 per week to maintain the machine and rent the space for it. What are the mean and standard deviation for y, the profit he earns from this machine in a randomly selected week? Well, the number of bars sold per week, I'm going to call that B, has a mean of 125. And a standard deviation of 7. What we want are the mean and standard deviation for y, which is his profit. Well, the mean for y is going to be the cost of each bar sold, which would be 0.25 times his mean number, or times his bars, the mean number of bars. And then we need to subtract that constant of $5. So, and I guess I could put that right in there. His mean was 125. So 25 cents times 125 bars on average, minus the $5 in operating costs, or maintenance cost. And then the standard deviation, when we're looking for that, we only are going to take the constant times the old standard deviation. We do not subtract the 5 because adding or subtracting a constant does not affect the standard deviation. And then if we multiply out, we end up with 26.25 for the mean and 1.75 for the standard deviation. So 7 should be E. Use the situation for the following two questions. A small local movie theater shows matinee movies during the day and primetime movies during the evening. Let M be the number of boxes of Junior Mints sold during the matinee movies. M is approximately normally distributed with a mean of 6.4 and a standard deviation of 1.2. Let P be the number of boxes of Junior Mints sold during the primetime movies. P is approximately normally distributed with a mean of 14.6 and a standard deviation of 3.5. We want the mean and standard deviation of M plus P. Well, the mean of M plus P should be the mean of M plus the mean of P, which should be 6.4 plus 14.6, which would be 21. And then the standard deviation for M plus P, well, we can't add standard deviations. So we are going to take the old standard deviation for M plus the old standard deviation for P and square them. So they are variances, but we want the standard deviation, so we're going to square root to get back. So 1.2 squared plus 3.5 squared. That gives us the new variance. Then we square root to get the new standard deviation. So I want a mean of 21 and a standard deviation of 3.7. Should be D. 9. What are the mean and standard deviation if the manager wants to look at the difference in sales, P minus M? Well, the mean of P minus M should be the mean of P minus the mean of M so it should be 8.2. But even though we are subtracting P minus M, the standard deviation is going to be the same. You still would find the variances, then add the variances, and then square root to get back to get the standard deviation. So I don't even need to recalculate. My standard deviation should be P minus M.